but you square it. I don't have the time to show you how these things are made up. I really don't. It's for a different class, actually. There's ways you do this. If you'd like to see that way, come and see me some other time and we can figure it out together. We'll just go through and invent them if you'd like. But for right now, just feel okay with this, okay? Also feel okay with this one as well, yes? Even if that's a constant, so...
These we should have memorized, I take it.
Yeah. Would you be able to follow that as well? If 1 gives you n, c gives you c times n, so c times 1, that would be the same thing. Let's do one very quick example on how you would go about doing this, but you'll see it's not actually that bad. It's plugging numbers in and then just manipulating those numbers. So you will have some homework on how to do this. Follow the appropriate form and see that you can actually manipulate them, because we're going to be using this in the next area idea that we have. Okay, what we're going to do is we're going to try to come up with the sum of that thing. What it actually equals, that's a number. So we're going to come up with a numerical expression that represents that thing. Now, give me some ideas. What you can and what maybe you can't do on this. Name one thing you can't do right here. What I haven't told you about. Can you distribute the k? I don't know. That's a good question. Can you separate by multiplication? As if they both involve a k, can you do that? No, not if our index is k, which it is. Right, these all match up. You can't separate that by multiplication. That's not in our property list. You follow me on that? That's a no can do on that one. Can you distribute the k? Yes, you can. So it's a function of k times a function of k. You can distribute that. That's okay. So that would actually be probably the first thing we would do. Because right now we can't use any of those closed form, that would be called closed form, the closed form formulas to work with this stuff until they look exactly like this or that. You got me? So, Joe's got a good idea. K squared plus k. Yes, no? Very easy. Name something, someone on the right-hand side of the room, name another thing that you can do right here.
Break it apart.
Say it louder.
Break it apart.
Sure, by addition, because we know we can do that. Hey, one thing real quick. Could I pull this k out in front of this?
No.
What if that was an x?
Yes.
Okay, very good. Do these fit now?
Yes.
Now we can just use the formulas. What's the n that I'm talking about? What is that n? That's just the number I'm stopping at. In this case, that's 10. So if we can figure out how to plug 10 into this one and this one, why these two? Hey, they match up. That's right there. I mean, that's exactly like what we have, only there's a 10. That's exactly what we have, only there's a 10. Plug the 10 in, and we can figure those two things out. So the first one gives us our k squared. We take, here's how you plug it in, 10, 10 plus 1, 2 times 10 plus 1, all over 6. That's from the first one. Then from the sum from 1 to 10 of k, well, we got another one for that. We got n plus 1 over 2, so that's 10. 10 plus 1 over 2. That's that one. Why don't you all figure that out and see what we got, okay? Go ahead and do that on your own. Do you guys understand where those numbers are coming from, first of all? This is kind of a basic concept, it's actually a little review concept, so make sure you get it before we go any further. What did you get? How much? 275. 430. Oh my gosh. Oh my gosh. I said gush. That's how bad it is. Oh my gosh. 440?
Yeah.
440. Let's get a quintuple check on that. How many we got 440? Okay. If you didn't get 440, hopefully you're wrong. Because that's what I'm putting on the board right now.
The real answer is 440 is now the right answer.
It is now. I'm not changing it. Hopefully you got it right. Whatever. Just get 440.
People at home.
People check your word. 440? Check your word. Email me. Call me later. Feel okay with our Sigma notation? How to manipulate it? Using our formulas? Those first three formulas are the ones we use most often for us. Are there other ones? Yes, but they get difficult. So we stick with those ones, otherwise the math just gets kind of tricky. We have a lot more time, so now we're going to start talking about how to actually find areas of under the curve of some sort of function. You got me? Remember how I introduced 4.1? I said there's two methods basically. Antiderivative method, which we've already conquered, but we don't really understand fully. Trust me, you don't, because you don't know where it's coming from. Second method is the rectangular method, it says how the antiderivative method comes about. I'll prove it to you why that comes about. You ready?
Yes.
So, area. Dun 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 dun.
Here for the candy games.
Yeah, I was thinking of coming up with calculus theme music, but I realized it's already been done. It's Empire Strikes Back, so.
And everything comes back to Star Wars.
Of course. I'm going to try to draw you some pretty pictures here, but I'm not much of an artist. Unless it's boxes, I can't do much with it. Let's say that we have some function f of x. I understand that I've given you this picture several times before, but I really haven't explained how to do it very exactly to the point, literally to the point on how to do it. That's what I'm going to do today. The idea that I gave you initially was, what if we were to cut this space into n equal subsections? The fact that it's equal just makes them easier for what we're going to do next. That's why they're equal. So basically we'd say, okay, I'm going to cut this into n equal subsections. So right over here, I'm going to make a little cut. I'm going to go over the same distance and make a little cut. Then another distance and make a little cut. I'm going to do this until I get however far away to be. So equal subsection, I'm going to find out the length and cut it into a certain number of subsections. You got the idea? This one will be our first cut, x sub 1, then x sub 2, then x sub 3, x sub n minus 1. Why n minus 1? Because the next one would be at b. That would be our last one. X sub n would be our last cut. My question is, n minus 1. Why n minus 1? Because the next one would be at b. That would be our last one. X sub n would be our last cut. My question is, can we find the width of each interval? The width of each interval. Are you guys okay on the x sub 1, x sub 2, x sub 3? That's giving us a certain number of cuts. Remember, a loaf of bread says however many times you cut it, you get that many more sections. So if I cut x sub n minus 1 times, I'm going to get x sub n actual rectangles. You follow me on that? So you slice bread, right? You cut it once, you get 2 pieces. You cut it 3 times, you get 4 pieces. Cut it x sub n minus 1, we get x sub n number of pieces, x sub n rectangles. The last cut would be at x sections. The width of each interval. Are you guys okay on the x sub 1, x sub 2, x sub 3? That's giving us a certain number of cuts. Remember, a loaf of bread says however many times you cut it, you get that many more sections. So if I cut x sub n minus 1 times, I'm going to get x sub n actual rectangles. You follow me on that? So you slice bread, right? You cut it once, you get 2 pieces. You cut it 3 times, you get 4 pieces. Cut it x sub n minus 1, we get x sub n number of pieces, x sub n rectangles. The last cut would be at b. That's where it would be. And that, there's nothing past that. So that would be the ending of our area. Did you follow? Now, the width of each little interval, we're going to call that delta x. Like change in x, delta x would be the change from a to x sub 1, or x sub 1 to x sub 2. So we'll call the width delta x. How would you figure out the width of each of those things? What would you need to know in order to figure out the width?
Total length.
You need to figure out total length. So someone right-hand side of the room, how would you figure the total length from A to B? Total length. How much? I need it in terms of what we have on the board already.
B minus A.
Say it again.
B minus A.
B minus A. If this was 10 and that was 3, your length would be? Sure, because you did 10 minus 3, right? Whatever this is minus whatever this is going to give me my whole length of that area segment. Does that make sense to you? Are you sure? Now, if that's the overall length, how do we find the length of each little interval? What do you think about that? Divide by the number of subsections. Can you tell me how many subsections I have here? I don't have infinite. No. This is finite number of cuts. X sub n minus 1. That's finite number. N minus 1 is the number of cut. Remember, we just talked about bread? We just talked about bread, right? If you cut a loaf, one slice, how many pieces do you get? If you cut it 3 times, how many pieces do you get? If you cut it 8 times, how many pieces do you get? Extrapolate that concept. You cut x to the n minus 1, how many pieces do you get? N. Do you understand we have n subsections here? N little intervals? So if you take the whole distance and you divide it by how many equal intervals you have, that's a division problem that says that I should have b minus a over n for my width of each little interval. Raise your hand if you understand that concept. That's kind of a key one. Do you understand where it's coming from? Are you sure, guys, over here? Yes? All right. Raise how many? So if you take the whole distance and you divide it by how many equal intervals you have, that's a division problem that says that I should have b minus a over n for my width of each little interval. Raise your hand if you understand that concept. That's kind of a key one. Do you understand where it's coming from? Are you sure, guys, over here? Yes? All right. Now, here's the idea. We're going to make some rectangles out of this. I introduced the idea already. We're making rectangles. We already have the bases of our rectangles. We got this and this and this and this, and they're all equal, right? That's going to make them very easy to add together later, which is nice. But what we've got to do is find out how tall our rectangles are, how high they are. Because in order to find the area of a rectangle, we're going to find the base, times whatever the height is, right? We need to find a way to find the height. Once we do that, we'll have all these rectangles, we'll add them together, it'll be very nice and easy. But here's how we're going to find the height. What you're going to do is you're going to pick an arbitrary point, somewhere in this interval. We'll call it, let me write it down first. Pick an arbitrary point. What's arbitrary mean?
Just random.
Random. You're going to find out that it's not going to make a difference at the end of our problem. Pick an arbitrary point for each subinterval. Bigger. Bigger's always better, right? So you can see it. You okay with that? Here's what we're gonna do. Pick an arbitrary point, some random point in between there. Now, I gotta explain to you why it doesn't have to be a specific point, but why it could be a random point. Because as soon as I start stacking infinite number of rectangles in there, as soon as I let my n go to 0, the width, let my n go to infinity, this distance becomes 0. Does that make sense? N goes to infinity, number of rectangles goes to infinity, the distance between them, finite divided by infinity goes to 0, right? Goes to 0. So that means that any point I pick is going to be really just squished. It's going to be bound between two numbers that are different. So it's going to be between there, certainly between, but it's not going to matter where it was because it's going to be squished in there no matter what, right? It's like trying to just put two hairs together and saying find the distance between them. Well, there's something in between them, but it doesn't really matter because they're so thin anyway. Who cares? So we'll pick some arbitrary point. Let's call it, that's a horrible line. That arbitrary point, we're going to call this x of 1 dot. Yeah, I know. It's weird.
Technical term?
Yeah. X1 dot. What the dot stands for is some arbitrary point. Doesn't matter where it is. And here we'll pick x2 dot. And so on, and so on, and so on. Here's what we're going to do with x1 dot and x2 dot and so on and so on and so on. We're going to take those values, the x values, plug them into our function, and that's going to give us the height at that exact point. Does that make sense to you? So what we're basically doing is saying, I want you to find the height here. I want you to find the height here. And I want you to find the height here at x3 dot. This one, by the way, would be xn dot, not n minus 1, that's the previous one. That's xn dot. That says that you have n rectangles. Do you see what I'm talking about? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, n. There you go. At each of those points, what we do is we say, all right, understand that this is the width of a rectangle right there. If I go up from this arbitrary point, it's going to give me the height of that rectangle. Do you follow that? You build your rectangle around that. So you go, okay, that's going to be the height of my rectangle. My next rectangle is going to have this height. My next rectangle is going to have this height. And you keep going all the way down. The last one would have this height. So we pick an arbitrary point for each subsection and make a rectangle. Now, I don't want to redraw this picture, so I'm going to go one more step. I'm going to show you why we do what we do. Okay, because I don't want to redraw this. I'm going to show you one exploded version of one of these rectangles. Understand that we can extrapolate and get this picture back from each one individually just by adding them together. Do you understand the concept of this first, though? Cutting this into equal subsections. Find the height of each one at an arbitrary point, then define the area. We'll just add up the rectangles. It will be an approximation for right now. I'll show you how to make it better later. Here's each rectangle. So the height of each rectangle. Let's say that I just take one of my rectangles. My arbitrary point is any x, whatever I'm talking about, k, dot. X of 1 or 2 or 3 or 4 or 5 or n, whatever that is, dot. Next time when we start back, we're going to start with this picture. We're going to find out the width of each one, which is already on the board. We'll find out the height of each one. Therefore, we'll be able to find the area since it's a rectangle, add them all up together, and you're going to see why we have the integral that we do from these areas. Did today make sense for you? The area since it's a rectangle, dot. Next time when we start back, we're going to start with this picture. We're going to find out the width of each one, which is already on the board. We'll find out the height of each one. Therefore, we'll be able to find the area since it's a rectangle, add them all up together, and you're going to see why we have the integral that we do, 5 or n, whatever that is, dot. Next time when we start back, we're going to start with this picture. Let's say that I just take one of my rectangles. My arbitrary point is any x, whatever I'm talking about, k, dot. X of 1 or 2 or 3 or 4 or 5 or n, whatever that is, dot. Next time when we start back, we're going to start with this picture. We're going to find out the width of each one, which is already on the board. We'll find out the height of each one. Therefore, we'll be able to find the area since it's a rectangle, add them all up together, and you're going to see why we have the integral that we do from these areas. Did today make sense for you? So we're right in the middle of trying to find the area under a curve, and what we've realized is that this is the second rectangular method. We're breaking up this area into equal width rectangles, and then we're going to find the area of each rectangle, add them all together. That should give us at least an approximation for the area under curve. Now, it's going to be a little off because, as you see, we're under and over the curve at certain spots. So this is going to be an approximation to start with. We'll talk about how to make it better later. I think I gave you a preview on that last time. What I've done here is I've taken one of our rectangles and we're going to try to find the area of one of these rectangles. So notice that we're somewhere within A to B. You follow me on that? Now I gave you some definition for the width of each of the rectangles last time. How much do we call the width? It was b minus a over n that gave us the width of each one, but we had a term for it. Delta x. That's the width of each subinterval. Did you follow me on that? So this width is delta x. Of course, it's important to have something that represents that because, well, we're going to take base times height to find the area of a rectangle, so that's important. Now, also, we called this, we had a point in here somewhere. Now, this looks like a midpoint, but it didn't have to be. What was that point? What was it? How do we find that point?
Was it an arbitrary point?
It's some arbitrary point. Arbitrary means it could be anywhere. Anywhere within that little sub-interval, and it has a dot. We call it x sub 1 or x sub 2 or x sub 3, whatever, but a dot, meaning an arbitrary point that's within that rectangle. In the first rectangle or the second or whatever the indices say, that's what we're in. So this is since I'm being kind of generic here, this is the kth rectangle, right? Whatever I'm talking about, the first, second, third, fourth, fifth, kth, whatever. This is the x sub k dot. That's the arbitrary point at somewhere in that rectangle. You feel all right with that? Now, how we used that arbitrary point, we just said, well, at that arbitrary point in my subinterval, what I want to do, I want to make my rectangle that height. That way I can have at least some stopping point. Not always the left, not always, it doesn't really matter where it's at, but at some point, I'm going to make it go up to the function, and that's where I'm going to draw my top of my rectangle. Do you follow that? Well, here's what we need to do now. We need to come up with some way to find the area of a rectangle. I just spoke about it, but how do you find the area of a rectangle? Base times height. Base is done. They're all going to be delta x. That's nice. What's the height going to be? The length of, would you agree it's the length of that right there?
Yes.
Where my arbitrary point is, right? Because remember, the arbitrary point gave us the height, and the height is based on the function. So if this is, let's call this f of x. Oops. If that's f of x, how tall is that?
F of x.
How would you find, so some people, I can tell you, you're a little bit lost on this. How could you find the height? Let's say that this point just happened to be 4. Let's just pretend it was at x equals 4. You'd plug in 4. Plug in 4 to what? So would you agree that if this was a 4, the height would be f of 4, right? If that was a 7, that'd be f of 7. Do you agree? Because f of whatever gives you the height of whatever. This is our whatever, xk dot. So the height of this rectangle, which means the height of this line is the height of the rectangle. The height of this line is the function's height at that point. The function's height at that point. F of xk dot. Yes, no?
Yes.
Yeah, the guys over here? Okay. So let's say this. Let's talk about the height of each rectangle. since we already did this, we know, well, the height of the first rectangle. Now this was every single rectangle we could think of, right, has this height. What's going to be the height of the first rectangle? Well, let's look at it. It'd be f of x1 dot, right? Whatever the first arbitrary point is, we go up to that height. That's the height of the rectangle. Make sense? That'd be the first rectangle. Then the second one will be f of x2 dot. And then so on, all the way when we get to f of x sub n dot. Our last arbitrary point that's somewhere between x sub n minus 1 and b, the ending point of our end. So that would be our last arbitrary point, xn dot. That gives us n rectangles. That's exactly what we want. You're still okay, yeah? Now the fun part comes. Everything's gonna make sense now. Oh, this is so cool. Aren't you excited? I'd be excited if I was in your shoes. Now, I'm still excited and I know how to do this, so that's pretty impressive. You should be excited. I'm building this up because it's gonna be very exciting. Exciting.
You're building it up too much.
Dang it, ruin the suspense. Area of a rectangle. You said this like 3 times now, but the area of a rectangle is base times height. Well, for each rectangle then, let's look at the base times the height. Would you agree the base is delta x for every single one of these rectangles? So here look. Here's the height of every rectangle, right? Here's the base of every rectangle. Therefore, the area of every rectangle would be f of x sub 1 dot times delta x. This is the area of the first rectangle. That's what this is. Area of the first rectangle. How about the area of the second one? Well, it's still base times height. How about the last one? Well, it's still base times height. You okay or not? Well, what have we done really? We've broken up, it's actually basic geometry, is what we've done. We've broken up this curve, the area under curve, the interval, into little equal rectangles, right? Well, actually segments. For each segment, we pick an arbitrary point. At each arbitrary point, we find the height, and to find the area, you multiply base times height. That's all we've done. Base times height, base times height, base times height for each individual rectangle. Now, since this is the area of each individual rectangle from 1 through n, and that encompasses all of them, how do you find the area of the whole thing? Add them up. So then area would be this. We add the first one through the last one. Yes, no? Okay, cool. Well, is there a better way to represent this thing?
Using our sum.
Using our sum. Yeah, using our sum. How would we use our sum? Is it going to be based on x or k? What are we actually doing? Are we changing delta x from rectangle to rectangle?
No.
That stays the same. In fact, if you wanted to factor it out, you could do that. It's in each one of them. Some people do that to prove this. But this is in every single one of them, so that can't change. Does the f change?
No.
Does the x change? The index of the x changes. The first one, the second one, the third one, the fourth one. So that's really the only thing we want to change. Where's the index start? 0 or 1 or 2 or 3? 1. Where's the index end? At n. So this area says I'm going to add up. What if you wanted to factor it out, you could do that. It's in each one of them. Some people do that to prove this. But this is factor delta on. We add the first one through the last one. Yes, no? Okay, cool. Well, is there a better way to represent this thing?
Using our sum.
Using our sum. Yeah, using our sum. How would we use our sum? Is it going to be based on x or k? What are we actually doing? Are we changing delta x from rectangle to rectangle?
No.
That stays the same. In fact, if you wanted to factor it out, you could do that. It's in each one of them. Some people do that to prove this. But this is factoring delta x from rectangle to rectangle.
No.
That stays the same. In fact, if you wanted to factor it out, you could do that. It's in each one of them. Some people do that to prove this. But this is in every single one of them, so that can't change. Does the f change?
No.
Does the x change? The index of the x changes. The first one, the second one, the third one, the fourth one. So that's really the only thing we want to change. Where's the index start? 0 or 1 or 2 or 3? 1. Where's the index end? At n. So this area says I'm going to add up. What am I adding up? Areas of rectangles. Going from, let's call it k, 1 to n. Do you know why we use k? We use the same symbol that we use there. That's x sub k, right? That means each individual one. We're just going to let this go from the first one to the second one to the third one to the nth one, however many we have. We say we don't want the f to change. We definitely don't want the delta x to change. That's not what we're talking about. What we really want to change is the index. I need you to understand where this is coming from, because if I could have just given this to you, right, and said, oh, here's your area. But that's pretty lame. So here's what this says. Well, you could probably figure it out. What's this part? Base. What's this part?
Height.
The height. What's this do? Adds them up. That's all it is. Height of each one, because we're changing it, right? It's just a quick way to write this. It's basically all we're doing. What this is, that's an approximation. That's based on a finite number of rectangles. Would you agree? Because you have to have a finite number for n if you're going to actually do this in practical application. Well, not practical application, but if you're going to do this and separate it into a certain number of rectangles, you'd stop somewhere. You'd say, okay, let's actually find this stuff out. And you'd go from 1 to 5, or 1 to 50, or 1 to 100. So what this gives you is an approximation based on n. So this is an approximation based on n. How many rectangles you fit into that little space. The more rectangles, probably the better. How can we make this better and better and better and better?
Make it approach infinity.
So basically make more rectangles, right? If you get more rectangles in a finite space, if I only had 2 rectangles in this space and I had some curve, probably not that great. But if I had like 500 rectangles in this finite space, probably better, right? If I had 1 billion, probably better. If I had close to infinity of them, probably the best we can get. In fact, it'd be so good there'd be no difference between the area under the curve and the area of my rectangles added together. That's the concept of a limit. Haven't we covered the limit before? It says if I let my n go to infinity, if I let my n go to infinity, that changes this from an approximation to an exact thing. So how do we make it better? How make it better? I'll make it better. That works for me, actually. I'm a math teacher. I really don't care. How make it better? Let n get bigger. Basically, let n get as big as you can. What that does is forces more rectangles into a space. Keep in mind that the rectangles are going to be the same width, right? So that means every time you force a new rectangle in it, they all get narrower and narrower and narrower until they have virtually no width. They have to have something, because here's why they have to have something. Can you find the area of just a straight line?
No.
You have to have something, don't you, to find the area. So you have to have a base, but that base approaches 0. I'll make it better. N goes to infinity. Here's how we make it better for us. We want n to go infinity. What's the only thing that lets us take n to infinity? We add limit. That's how you find an exact area. Now I'll tell you a little secret. This right here, this is an integral. Here's why it's an integral. A sum, you see the sum here? We take a sum to infinity. Remember how I told you the integral was elongated s? That stands for that. So, limit of a sum is how you get that. Function, that's some f of x. Delta x, dx. Basically the same idea. Okay, that's where the symbols are kind of coming from. The integral does mean a sum. It means when you're adding up all the rectangles of some function, and that's the width of a rectangle. Basically, that's you can translate that.
So those 2 equations are the same?
That's what we're doing.
Okay. I just got lost there for a second, sorry.
Yeah, well, remember we talked about integrals are antiderivatives, but they also mean the area of under a curve, right? This is the area under a curve. They're the same construction. The difference is, well, we use different symbols. Instead of a limit of a sum, and you just call it integral. It really is a sum. It's a giant S. It's called a sum. The integral just means, in the terms of a definite integral, it just means you're actually finding the area. So there's a little more to it than that. Basically, that's the idea. Now, back to how to use that thing, because you're going to have to do it. You're going to have to use this to be able to find some areas. Would you like to see how?
Yes.
We generally choose xk dot to be one of 3 places. You can choose it to be anywhere. Arbitrary point. Could be the far left of the subinterval. Could be like way over here. It could be at the left. Could be the far right, could be at the right. Could be the middle, could be anywhere in there. It doesn't matter. Why does it matter? How wide is this getting to?
0.
It's going to 0. The width is going to 0. That means no matter where your arbitrary point is, it will be squished, right? It's basically just in the middle view. Anywhere in there, it doesn't matter. The arbitrary xk dot to be one of 3 places. You can choose it to be anywhere. Arbitrary point. Could be the far left of the subinterval. Could be like way over here. It could be at the left. Could be the far right, could be at the right. Could be the middle, could be anywhere in there. It doesn't matter. Why does it matter? How wide is this getting to?
0.
It's going to 0. The width is going to 0. That means no matter where your arbitrary point is, it will be squished, right? It's basically just in the middle anyway. So it doesn't really matter where it's at. What we choose it to be is either the left for all of them, the right for all of them, or the middle for all of them. That way we're more consistent and we can work our formula better. Does that make sense? You don't want to pick arbitrary and have them all random because it'd be hard to do the next thing we're doing. So in general, we typically choose our xk dot. Choose? Chose.
Choose.
Choose me. Choo. I get it. We generally choose xk dot to be left endpoints, right endpoints, or midpoints of each subinterval. By the way, your book has a tendency to call this xk dot c sub k as well. So if you see the c sub k, we're talking about the same thing. I prefer the xk dot. I think it looks better because you have it in terms of x. I like that better. The book uses c sub k. So whenever you're reading, it's a c sub k, I mean xk dot. They mean the arbitrary point, the point in there, either left, mid, or right endpoints. Do you follow me on that? So when you see c sub k, that's what they're referring to, is the left, the mid, or the right endpoints. Same thing we're going to be referring to. Now, here's how to do it. Let me give you an example. When you're talking about area, you're talking about a finite thing, right? Your area doesn't go on forever. It starts and it stops somewhere. It starts at A, it stops somewhere at B, wherever B happens to be. What we're doing here is we're starting to make cuts. Wherever our delta x is, that's where we're making our cuts. So we'd make a cut here, and a cut here, and they're all equal. And a cut here, and a cut here. And those cuts would be x sub 1, and x sub 2, and x sub 3, and x sub 4, and x sub 5, and so on, and so on, and so on, and so on, and so on. Can you please tell me the distance here? Oh, don't overthink it. What's the width of every single rectangle we have? Delta x. What's the width here? Oh, good. Don't overthink it. What's the width here? Very good. Within each of those cuts, we would make a little arbitrary point, right? This would be like our x sub 1 dot. That would be the arbitrary point that we're talking about. Does that make sense? And in here would be x sub 2 dot. And so on and so on and so on. So arbitrary points will be somewhere in there. Now here's the point I'm trying to make. Your arbitrary points are either going to be, look here, your arbitrary points are either going to be your left endpoints, that would be here, and here, and here, and here, and here. See how we have each interval? That would be the left endpoint starting here, and here, and here, and here. The right endpoints would say, oh, for each interval I'm going to start the right. Here, and here, and here, and here, and here. Does that make sense? The midpoints would be kind of what this one looks like. It would say here, and here, and here, and here, in the middle of each of our little areas. We only need one, because no matter what, we're going to go up to the function, right? And that's going to give us the height. So for each interval, you just need to be here, or here, or here. That's typically what we do. It could be anywhere, but we choose lefts, left, left, left. We choose rights, right, 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 or we choose mid, right in the middle of it. Here's how you find out each one. I'm hoping that you can walk through this with me and understand where they're going. Let's talk about the left endpoints first. Then we'll do right endpoints and finally midpoints. So in each case, we'll have an xk dot. By the way, some of this might be a little vague to you until we actually do an example and you see how to use the xk dot, but ultimately we're trying to do this. Look up here for a second. We're trying to figure out a way to substitute this into this, because we need to have some sort of expression that represents it, right? Otherwise we can't plug it into our function, and then we can't do anything with it. So we're ultimately trying to do that, trying to get some expression for xk dot, plug into our function. After we plug in our function, we'll have something in terms of x's and things like that, and k's. So, and that's what we want, because we need x's and k's to deal with our summation. And we need that to deal with the limit. So that's the whole idea here. So far, so good? Yeah. Okay. Very good. So let's talk about all these. Do an example, you see how to use that. We'll have an xk dot. By the way, some of this might be a little vague to you until we actually do an example and you see how to use the xk dot, but ultimately we're trying to do this. Look up here for a second. We're trying to figure out a way to substitute this into this, because we need to have some sort of expression that represents it, right? Otherwise we can't plug it into our function, and then we can do anything with it. So we're ultimately trying to do that, trying to get some expression for xk dot, plug into our function. After we plug in our function, we'll have something in terms of x's and things like that, and k's. So, and that's what we want, because we need x's and k's to deal with our summation. And we need that to deal with the limit. So that's the whole idea here. So far, so good? Yeah. Okay. Very good. So let's talk about all these. What are we going to let these things equal? And we're talking about left, right, and midpoints respectively. Let's talk about the left endpoints. Where does this whole thing start? Not at 0 or anything like that. At what? It starts at A. Wherever A is, that's where our interval is going to start. Agreed? So each of these is going to have an A. You know, maybe I'll do the right endpoints first. I think you'd probably understand that a little bit better. We start at A. Let's say that I wanted my endpoints to start at the right of each subinterval. So for right endpoints, do I want to start here for my very first one, or here for my very first one? This one. So I'd have to add something to get from here to here. What am I going to add? It's already on the board. What am I going to add? Okay, so would you agree that to get to a right endpoint, I'm going to add delta x? Yes or no? Mm-hmm. So to get from here to here, I don't want to start at A. For right endpoints, I don't want to start at A. I want to start at x1. So I'd start at whatever this is, but plus delta x, right? The next one, how far, now this is going to seem weird because I'm going to go back to here, but how far away is the next endpoint from here?
A plus 2 delta x.
2 delta x is away. How about the next endpoint?
A plus 3 delta
3 delta x, and 4, and k. Yes, no?
Yeah.
Can you see how that works? I've gone over your head, some of you. Can you stand up so I don't go over your head? Just kidding. we're trying to find segments that are delta x away, right? Delta x is the width. If I'm talking about right endpoints, I say, how do I get from one place to the far end of my subsegment, my subinterval? Well, I'm going to add delta x to it. If I start off with this plus delta x times 1, because we start at 1, right? That's going to give me this point. Then 2, 3, 4, 5, 6. Notice how I've gone 1, 2, 3, 4, 5, all the way to n, and each of those will be the furthest most right point on each of our intervals. Yes or no?
Yes.
Okay. That's for right endpoints. Let's talk about left endpoints. Left endpoints, I want to slow this down by 1. Because what I want to have happen is, I want to start here, right? And then on my second one, I want to be here. Does that make sense to you? I hope I haven't lost you, I really do. Right endpoints would be here. Right, 1. Right, 2. Right, 3. You get it? Left endpoints, that would be a plus delta x for the first one, a plus 2 delta x for the second one, a plus 3 delta x for the third one, a plus delta x times k for any of them. That's right endpoints. Left endpoints would do this. Left 1, left 2, left 3. Do you get that? So, what's going on? I'm actually hitting pretty much the same exact values, aren't I? Except I'm starting one earlier. I'm starting on my A. So I need to slow this one down by 1. If I slow this one down by 1, I'll have my left endpoints. How do I slow this one down by 1?
K minus 1.
Subtract delta x with the same thing as subtracting 1 from k. You have it right. If I do that, subtracting 1 from k. So for instance, how do I get from to here? I'm going to add basically, I'm going to add 0 delta x's. 0 delta x's. That would be, because we start at 1, k minus 1. You okay with that? Have I lost you? Notice that k always starts at 1 for us, right? K minus 1 is 0 in this case, so 1 minus 1 is 0. 0 times delta x is 0. You would start at a. You with me? The next one would say, okay, plug in 2. 2 minus 1 is 1. You would have 1 delta x away for your second endpoint. Ah, that's right there. Third, fourth, fifth. So I basically just slowed it down by 1. You okay with that? Now the trickier one. Midpoints. Not really that bad. Not really that bad. This would be midpoint 1, midpoint 2, midpoint 3. Here's the question. How much of delta x am I adding to get from here to here? I'm adding half of it. That's exactly what it is. It's a little bit weird though, because you're going to take it and say, you've got to have the same delta x, right? So you're going to have that. Subtract 1/2 from k and then multiply it. So take 1 minus 1/2, you get 1/2. You're adding half of delta x. 2 minus 1/2, that's 1.5. Then multiply by delta x. And that's what you're doing here. And that's the idea. But you have the idea, basically down. In fact, I think it might work a little bit better. Would you mind if I switch those around? So instead of having delta x k minus 1, I think I'd like to keep it k minus 1 delta x. I believe that's how perhaps your book has it. K times delta x. And k minus 1 times delta x. By show of hands, how many people understand the endpoints? And lastly, you might also see this as C of k. So note that that's the same thing as what we're talking about. So when you see C sub k, that's the identical. Now, would you finally like to see how this is put into practice? Would you?
Sure.
I was hoping you would. Otherwise, I've got nothing. So that's good. My lesson would kind of fly a little bit. So good thing you want to know. You understood the idea, right? Areas? It's kind of cool. It's an interesting idea, isn't it? To take all those, make them really small, add them together. We have it. We can do that now because we have this idea of a limit. Limit basically gives us the idea of calculus. That's it. That's it. I know you think it's a derivative, but derivative is based on limits, right? I know you think it's an integral, but integral is based on limits, right?
Yes.
That's all it is limits. Adding things together. So, let's see if we can add these things together. We'll start off kind of simply, just so you get the idea of how to do this. The process will be the same. As you guys have found out, sometimes implementation is more difficult, but the process is the same. Some problems are harder than other problems, clearly. But this one shouldn't be too bad. It'll give us a nice understanding about what's going on here. Let's go ahead and find the area. Under f of x equals x squared on 0 to 1. And what I'm going to, in general, in your real life, you can pick whatever endpoints you want. It really doesn't matter. It will all work out the same. What I'm going to tell you is in what endpoints to pick. In this case, I want you to pick right endpoints. Again, it doesn't matter when you're taking a limit, because n's going to infinity, it's all getting squashed anyway. I would say it looks like right endpoints tend to be the easiest for me. So I don't have to deal with this, I don't have to deal with that. Just pick right endpoints. Ready to get down to it? The first thing you do, whenever you're doing this, you have to have, we're basically trying to fill this out. So we're going to start on the right, we'll work our way left. You got to start and you got to know what delta x is. So delta x, recall that delta x is, how do we find delta x? B minus a over what? Okay. So this is like step number 1. In our case, delta x. By the way, that was my fraternity, so I always liked writing that. Delta Chi was the fraternity I was in. So every time I write that, I'm like, woo! Yeah. No, actually, I don't even care, but it's kind of fun.
Wait,
I was in a fraternity.
That was your fraternity?
Mm-hmm. We didn't call it Delta X. It was Delta Chi. It's Chi. Anyway. Fun times. Fun times. What's B in this case? How are you getting the 1?
B minus
Okay, this is B minus A, that's right. The interval tells you A and B, right? So where you start is A, where you stop is B. Where do we stop? 1 minus, what is your A? I need more than this, guys. More than this. Come on, y'all should be participating here. If you don't see where it's coming from, tell me. That's fine. But don't just sit there silently. Do you see where the B's coming from? You see where the A's coming from? Okay. What's the N? I don't know. We can't do that because we're letting N go to infinity later. So we don't know what N is. I'm not telling you 5 or 6. We want better than that. We don't want approximations, we want exactness. So we need to have an N up there. Do you feel okay that this is going to equal 1 over N? Yay or no? Okay, cool. The next thing you have to do is you have to come up with some representation of your xk dot. You need that because we have now our delta x. That's great, 1 over N. We now need our xk dot. Xk dot. Oh, let's do the xk dot. I said left, right, or mid. Which are we doing?
Right.
So you'd go over here. You'd find which one is appropriate for you based on what the problem is telling you to do. Sometimes in your book you'll get mid, sometimes left. In this case I'm giving you right. So we're going to do this exact same thing. So in our case, because we're right, not all the time, but because we're right endpoints, we've got A plus K delta X. By the way, this order is non-negotiable. You have to go in this order. You'll see why right now. So for us, xk dot equals, how much is a?
0.
0 is nice. Oh, I love 0. Plus. Do I have anything up here that says k in it? Do I have any numbers for k? Then leave it k. Times. Oh, that's a delta x. Have you found out what delta x is yet? That's why you have to do it first, because you're going to be using it in your next step. Anywhere, you're going to be using delta x. It was 1 over n, which means for us that we're going to get k over n. By the way, this becomes fairly harder when you don't have a 0. Okay, fairly harder. If you have a 0, it's kind of nice. Why? Well, we had 0 to anything, gives you anything. But the next step means that having a number over here could potentially make it a lot harder, because the next thing we're going to do, we have our delta x, right? We actually used it. We have our xk dot, yes. What does f of xk dot mean?
Put that into our function.
You plug it in to the function. So step number 3 says, I want f of xk dot. In our case, that's this, folks. Look, go slowly. What was showing me every step? That's f of, what is xk dot for us, ladies and gentlemen? What is f of xk dot? K over n. So we're going to take f of k over n. Oh my goodness. How do you take f of something? What if that was f of 5? You should be able to tell me right now if that was f of 5, what you would have.
25.
How are you getting 25? That's because it's f. It says take this, plug it in. That's a composition, substitution. So this says you're going to take whatever's in here, and based on our function, you're going to square it. Do you now see why if you had a constant up there, it might make things a lot harder?
Yeah.
Because if you have to square something with a number, that's distribution. If you have to cube something with a number, that's a lot of distribution. That's a pain, right? Good thing we have integrals, because I just told you ahead of time that this translates into an integral, so we can do this. But this is the idea on how it works. This is it.
Are we going to see doing this mainly through integrals, and we're just proving the integral, or is this what we're going to usually be solving?
You're going to be solving with this for right now. We'll translate to a definite integral later. For right now, you kind of need this concept now. Are you okay with this so far? As soon as you have your delta x, great. You can find your xk dot, no problem. As soon as you find your xk dot, okay, you can find your f of xk dot. Now the last thing we're going to do, take all this stuff, put it right up there, and we'll have enough to do our integral, I'm sorry, our limit of our summation. You ready for it? No? Can you make it down this far?
Yes.
It's not too bad, really. Just follow the steps. 1, 2, 3. Step number 4, important step. Don't worry about the limit yet. Don't worry about that. Not yet. You're welcome. Fill this whole thing out. If you fill that whole thing out, you can't change the sum. However, you do have expressions for this and for this. What did we find out was our f of xk dot? All said and done, what was it? K over n what?
Square root.
Okay. And we also should have an expression for our delta x. What was our expression for delta x? 1 over n, I hope. 1 over n. For delta x, 1 over n. I need a show of hands if you see where those things are coming from. Okay, it's still another substitution. But now we're pretty much good to go. What we're going to do, you'll have practiced this, by the way, on some of your 4.3 homework. What you're going to do, get rid of that square. Work this thing down, make it look nice. How do we make it look nice? Well, you use those properties that I told you last time. here's the properties I told you last time. These are important ones. The important properties are, you can pull out any constants that you want. A constant is defined as not being your index. Your index is k's. K's. I don't care about the n. K's. You got me? It means you get to pull out x's and anything else that's not a k. And you can separate by addition and subtraction. That's the only two that you get to deal with. So in our case, what's nice about this is, which one of these, well, after we do the next step, you'll see it. Which one of these things, when I write this, as k squared over n cubed, which one of these things can I pull out? The k squared or the n cubed, or either, or neither, or both? Can I pull out the k's? The k's? The k has to do with my index. I can't touch that. Can't touch this. Okay? I'm not wearing my Hammer pants, but that's the song. Are you guys too young for MC Hammer?
No, I'm not.
Sweet. Now, n cubed, I'm only 21, so I'm a little young for that. The n cubed, that does not deal with k. We're talking about that k right there, not that n. Everything's going to n. That you can pull out. Is it n cubed or 1 over n cubed?
1 over n cubed.
Can somebody please tell me why we did this? Why in the world did we do this? Does this look familiar? Yeah, that's why we did that. Notice what we did. This is kind of crazy, but we've changed this entire ugly, nasty, weird thing into, nice. You have a formula for that. In fact, the formula for that do you remember it?
Something over 6. It is n times parentheses n plus 1, n parentheses, new parentheses 2n plus 1, all over 6.
I didn't hear a word of that, but I'm just going to do it on my own. The 1 over n cubed stays the same. I was focused on something else. Times the summation from 1 to n. You have this in your book. I've given it to you before. I think you were probably right if you just read it off that. It's n plus 1, 2n plus 1, all over 6.
Yeah.
Why is it nice that we could pull this n out? Well, look at that. That's the same exact n, right? Same n. That's great. That's so convenient for us. What are you going to do now? Probably make it a little bit prettier, I would say. I would say that this is being multiplied, so I know I can eliminate that n and make that a 2, right? Could do that. Before you start distributing, you might want to do things like that, right? That'd be a lot better. Are you still okay so far? How many of you feel just fine with this thus far? Now you'd probably distribute. Why don't you go ahead and do that? I hope I'm right. Am I right? Yeah. I love being right. That's great. Did you get the same thing?
Yeah.
Now, those of you who have been paying attention up here, what's the one thing that we haven't done yet?
The limit.
The limit. Oh, we've done this, we've done this, we've done this. In fact, this is this. That's what that is. Right? That's what we've done so far. It doesn't look like it because we used our formula. That's great. It's kind of nice. We haven't done this. So before you start writing an A, we're not at the A yet. Here's the 5th and final step. Take a limit as n goes to infinity. That's it. Notice the variable we ended with. That's kind of cool. We want n to go infinity. What's the only variable we have? Fantastic. That's great. Why is that going to happen? Because you're actually going to numbers. If you're going to numbers, you need to end with a number, right? If there was x's up here or anything, yeah, that you'd have x's within your problem, but we don't. We're going from 0 to 1. That's called a definite integral. You get the number. So we'll take a limit. That's great. Right, that's what we've done so far. It doesn't look like it because we used our formula. That's great. It's kind of nice. We haven't done this. So before you start writing an A, we're not at the A yet. Here's the 5th and final step. Take a limit as n goes to infinity. That's it. Notice the variable we ended with. That's kind of cool. We want n to go infinity. What's the only variable we have? Fantastic. That's great. Why is that going to happen? Because you're actually going to numbers. If you're going to numbers, you need to end with a number, right? If there was x's up here or anything, yeah, that you'd have x's within your problem, but we don't. We're going from 0 to 1. That's called a definite integral. You get the number. So we'll take a limit as n goes to infinity, and if you remember anything about limits, which is why we did this, it was just a little while ago, 2n squared plus 3n plus 1 over 6n squared. Some of these basic polynomial types are very easy to find a limit of. When we go n to infinity, what do we do? What was the idea?
Look at our
Largest power in the denominator, and you divide everything by it, right? In other words, you look at the leading coefficients. The leading coefficients are the coefficients of the terms with largest power. So leading coefficients here are 2 and 6, respectively. Notice how the powers match up. If you divide everything by x squared, the only things you're going to be left with are 2 and 6, and everything else is going to go to 0. I'll show you that step right now, but basically I know this area is 1/3, right now. 2 over 6 is 1/3. Here's the work that you would show. You'd say, oh, okay. That's a limit. That over n squared. That over n squared. That over n squared. and 6n squared over n squared. Do you remember me teaching that from a while back? And what we do is we simplify what we can. These n squareds are gone. These n squareds are gone, but this one's not. That just becomes an n. So this is the limit of 2 plus 3 over n plus 1 over n squared all over 6. Tell me what happens when you let n go to infinity. Does the 2 change? Does the 6 change? What does this become? 0 and 0. Perfect. That means the area, because that's our definition for an area, is 2 plus 0 plus 0 over 6, or in other words, the area is 1/3. And that's how you can find the area under a curve. We just completed the whole process right here, folks. We have functions. We find rectangles. You use right endpoints or left or midpoints. Use a limit on them. I've given you every step now, right? You have 5 steps. I hope that's clear for you. Keep in mind that on your homework, this is often called C sub k. You can call it C sub k as well. That just means an actual value within your interval. That's some solid number that you're plugging in.
Is that it?
Good afternoon. Hope you're doing well. We're going to continue talking about how to find areas using these limits and basically by adding up rectangles. However, before we get on to another example, I do want to discuss what it is we're actually doing. What we're doing is we're figuring out something called net signed area. We are actually not calculating total area right here. We're calculating something called net signed area. Would you like me to explain the difference?
Yes.
Here's what net signed area says. Before, every function we've had till right now, figuring out the area, has been completely above the x-axis. You might not have realized that, but we haven't had one that's below the x-axis. Here's what net signed area says. If I have this curve, and let's pretend that the horizontal is the x-axis, how many areas do I have? Distinct areas. There would be 3. Between the function and the x-axis, there's area 1, area 2, and area 3. Here's what net signed area says. It says the area that's above the x-axis counts as positive area. Area below the x-axis counts as negative area. That's just how this area works. It says this would all be a positive area and a positive area, but this would have a negative area. Now, in order to figure out total area, I'm going to show you how to do that in a couple more lessons. But right now, just know that when we're calculating area from one point to another, it is including this as being positive, this as being positive, and this it would count as a negative area. It would subtract from the 2 positive areas. Are you following me on that? So the area you get with doing this method, even if you don't have a graph of it, even if you don't know what it looks like, here's what it's doing. It's saying the total area is the positive areas minus the negative area. Or the area above the x-axis and taking away the area below the x-axis. That's what that actually means. It's basically the difference between the areas above and below the x-axis. The difference between the areas above cumulatively and the areas below cumulatively of the x-axis.
Is symmetry a factor?
Not really. I guess it could be. It's found exactly the same way. So the area formula that I created with you guys, remember the area formula that I created with you guys? Hopefully you've been using that. It's the limit with that sum. That doesn't change. This is, when I said area, what I meant was net signed area. I didn't mean total area. We'll talk about that later. So when you're calculating area like this, which is basically what we've been doing for the past couple days, also, for those of you who have been doing your homework, do you realize that this is in the book represented as C sub k? You've seen that as well, right? It means the same thing, right? So I could use that interchangeably. That is net signed area. What we've been doing is net signed area. Let me show you an example of this so you can kind of get an illustration. Of what I'm talking about. Would you like to see that? We're going to do one kind of quickly. We're going to go through it very fast because the process doesn't change, but I want to show you at least one time. Okay, we're going to find the area. area of f of x under f of x equals, what did I say, x minus 1 on the interval 0 to 2 with left endpoints. That's what we're going to do. Hey, what's the first step? I think I gave it to you. First step, number 1.
Delta X.
Okay, let's find delta x. I'm going to outline all these steps for you just like I did before. So delta x. In our case, delta x is, how do you find delta x? Come on, people, help me out.
Minus A over N.
2 minus 0 over n. It should have an n in it. 2 over n. That's always your first step. You got to have that before you go any further because the next step uses delta x. The next step is you got to find c sub k or xk dot, whatever notation you prefer. I don't care how you do it. I've called it xk dot in the previous lessons. The book will call it c sub k. Would you like me to use c sub k so you kind of see that? Okay, I'll use c sub k if you like. So the next is find c sub k.
Left endpoint.
Using left endpoints, c sub k says this. A plus k minus 1 delta x. That's what c sub k would say for you. Didn't I give you those formulas last time?
Yeah.
Okay, so you look up the correct endpoint, whether it's left or right or perhaps a midpoint, and you use the appropriate formula. You with me? Then you fill out everything that doesn't have a k. The k is going to stay. There's a plus k minus 1 delta x. That's what c sub k would say for you. Didn't I give you those formulas last time?
Yeah.
Okay, so you look up the correct endpoint, whether it's left or right or perhaps a midpoint, and you use the appropriate formula. You with me? Then you fill out everything that doesn't have a k. The k is going to stay. There's nothing you plug in for k. You're going to use that because your summation is using k. Okay? Okay minus 1? Whatever. So in our case, c sub k is, what's your a?
Zero.
A is where you start. What's your a, folks? Come on.
Zero.
Plus, what do I plug in for that k? Nothing. You're going to use that later on because you're going to be basing your summation notation on your k, right? You'll have a formula for that later. It has to have a k. Well, not have to, but it's most likely going to have a k. K minus 1. Now your delta x, this is why we did this. Delta x is 2 over n. So c sub k, 0. 0 does nothing. You have 2k minus 1, don't distribute, over n. Don't distribute, and I'll tell you why later. You're just going to have to re-factor out anyway if you do distribute. Raise your hand if you feel okay with this so far. Good deal. Basic right now. What's step number 3? Come on, we're on a roll.
So find the function of c sub k. Or find.
Good.
Plug
Sure. Or xk dot, which is what we used before, to show the arbitrary point. I like the xk dot because it means arbitrary. That's why I showed it to you initially. But the c sub k says the same thing. It says, can you find out, using our arbitrary point, what the function is going to look like? What is the function, ladies and gentlemen?
2 over.
No, the function.
Oh, function.
X minus 1. So I'm supposed to take c sub k and plug it into that. You with me? That says f of 2 k minus 1 over n, which means that I'm going to have, well, if our function is x minus 1, it says 2 k minus 1 over n minus 1. Would you raise your hand if you feel okay with that so far? I guess you could have distributed, you might do that now. There's a couple ways we could do this problem, if you'd like. Probably the easiest way would be combine everything right now. Get one fraction out of it. So, what's the next step after that, after we find our function? Do what now?
Multiply by delta x.
Aha. Right now we have this, okay, we've got our function. The next step, step number 4 is, you're supposed to put this in your summation, right? 1 to n. You're supposed to make that. You're supposed to say, okay, I know my delta x, I can plug it in. I now have my f c sub k, I can plug that in, and then we'll take the summation, try to work that on out, and see what we get out of it. Nudge your head if you're okay with that one. Let's plug that in together. What goes in place of the f of c sub k? Well, what is your mumblings? What are you saying?
That.
Function of c sub k.
Very good. Yes. The function of c sub k. Come on, Leonard, it's right there. Sure, just like that.
Parentheses.
Parentheses is good. We need that.
Times delta x.
Yes, you don't want to miss your delta x. That's important, especially for us. Our delta x is 2 over n. Would you raise your hand if you're okay with this so far? So far. Yes, everybody? So you're okay that where we got the delta x, right? B minus a over n, that's just going to be 2 over n. You okay with the c sub k? That's xk dot, the same thing. That means you're going to use a formula there. It's going to be either left, right, or mid. We have left in this case. That's why we use this formula. Remember that the right would have no minus 1. The mid would have minus 1/2. And you do the same exact thing. We figured that out by inserting our delta x. Then we take this value, our c sub k, plug it into our function. That's right here. And we're going to get this minus 1 for our function of c sub k. That's why we have that right there. That's where the minus 1's coming from. It's not magic. It's because I have x, that's treated as my x, minus 1. Got it? Then we plug everything in. We got our function of c sub k. Oh, that's here. Times our delta x. We got our delta x from right there, and now we're good to go. What now? Well, now you work with it. Now you do some algebra. Probably have to distribute that. You do have to distribute this one. So we're going to get stick with me here, folks. 4k minus 1 over n squared minus 2 over n. Are Are you okay with that? At this point, you have, well, next one's not an option, but the one after that, you're gonna have an option. The next thing you do is you break up those two sums. Do you see how we can break up the sums by subtraction? That's always legal with subtraction and addition. So here you'd go, okay, summation notation k equals 1 to n. This minus this. Are you still okay so far? You sure? At this point, you do have options. Your options are this. You could distribute the 4. You could distribute the 4 and then separate those fractions and make 2 more sums. You could do that. That's option number 1. That's a decent option. Option number 2 is, notice how this and this are not based on k. You can pull those out. And then you could separate the k minus 1. You could do that as well. Just make sure that you have a bracket around the whole thing. That way you don't miss anything about it. Are you seeing what I'm talking about here? So that option's up to you. What do you want to do? Do you want to distribute right now, or would you rather pull this stuff out? If you want to break it up, why don't you try it? Some of you who feel like distributing and then breaking it up, go ahead and do that. You pull this out?
Yeah.
Okay, we could do that too. That's probably the way I'll choose to do. So I'm going to look at this one. I'm going to say, all right, well, I know this is 4 over n squared. And right here, I'm going to put a bracket around this so I don't forget it. I can't forget that. I'm going to group that to say, yes, that's the sum of that whole thing still. Minus, oh, well, wait a second. How about that? What can I pull out of the 2 over n?
1n.
Say what?
1n.
What about the 2?
Yeah.
Pull 2 out, 2?
Now, can you combine the 2n you pulled out and the 4n over 2?
You'd factor it and get pretty messy. I wouldn't recommend that. Okay? Because this is different.
That's where I messed up on the whole
Okay. You can't combine that right now. Can you make it that far though, algebraically? The next part is make your sums something you can do with. This is not something you can deal with right here, but if you split that up, notice how we're going to keep it inside the bracket. You see why we're going to keep it inside the bracket? Because ultimately our answer is going to get multiplied by 4 over n squared, yes? So we're going to have that. We'll have the summation of k, of course k is going from 1 to n, minus the summation of 1 from 1 to n. It's in a bracket. You have to have it. Minus the same. Same thing, I haven't changed that at all. But now's the good part. Now's the part where you actually get to do some nice stuff. You ready to do some nice stuff with it? It's time to get rid of all those summations, because we don't like those. Those we have formulas for. You ready to deal with the formulas for those? You sure? Real quick though, how many people feel okay with this so far? Feel just fine with it? So you see where all this stuff is coming from? That's great, that's great, okay. Now, have you memorized or do you know the formula for sum of k?
Yes.
Times n minus
Plus one over two.
Sure. All the mumbling hopefully made over 2. Good. Yeah, I think I heard most of what you said. That's that. That is this. Minus, it's still in a bracket. What's this? We talked about that only one time. It's
Constant times n.
constant times n, which would be what?
N.
Just n in this case. Minus 2, okay, 2 over n times, how much is this one?
N.
N, yeah, n. That's why, by the way, it's, in your notation, it says sum of c is cn, because you always pull the c out, right? The summation of 1 is always just n. That's why it's cn. So this is going to be n. I do it that way because it's kind of nice. You can see what's going to happen with that. You still all right? Let's keep going. Let's do some fancy math. Easy part, I'll do this one for you. I'll tell you what, the n and the n here, I get to cross those out. Cool, right? Done. That's nice. What's going to happen with this whole garbage?
You gotta distribute your n.
Probably distribute that. If I distribute that back in there, I needed to factor it out to get my summation notation okay, but now I need to distribute it back in. If we had split this up, we probably wouldn't have to distribute that back in. So it's up to you what you want to do with that. But notice how if we would have distributed here, split our fractions, then pulled things out of each individual sum, there'd be no need for distribution later. Do you see the difference in that problem? So it's 6 to 1, half dozen to the other. It really doesn't matter what you do. You're going to have to factor and distribute in both cases. So here we'll get what?
N over 2, n squared over 2.
Okay, let me do this a couple steps because I'm thinking you're going too fast for me. How about that? Does that work for you? Yes, no? I haven't simplified anything yet except for these two ends. Is that okay? Are you sure? I'm getting nothing. I need more than this, guys. I need yeses or nos. That's the only way I know how to teach. I need mm-hms or mm-ms, not. Okay, that doesn't work. Do you get it or not? If you don't, that's not a problem. You should let me know. Now, let's simplify some other stuff. Tell me something that simplifies here. Okay, cool. So the 2 and the 4, those simplify. The n and one of those n's simplify. What simplifies here is an n with the square part of that. So I get 2n plus 1 over n minus 4 over n minus 2. We're almost done. Almost done. You ready for it? Now, we'll distribute the 2. We'll get 2n plus 2, and I'm also going to break it up. (2n plus 2), and then I split the fraction up. 2n over n plus 2 over n. Yes, no? Just some basic algebra, but I want to make sure you're really solid on this before we go any further. Are you really solid on that?
Mm-hmm.
What's nice about this, we're going to get, that's going to be 2. Got it. Man, we're almost done. Why don't you tell me the next thing I'm going to have up here? Oh, come on. What's the next thing that happens? You see something up here?
2 n's cancel. 2 over n. And you're positive, negative 2 and you're positive.
Oh, so 2 and negative 2. Oh, I made a mistake. Why did you let me do that?
Oh,
I was wondering what you were talking about. Okay. What is this math? Anyway, the 2's are gone. We have 2n minus 4n. You okay with the 2n minus 4n? Right. Now, what do you do when you have made it down that far? You have step number 5. What are you supposed to do now? A limit of the whole darn thing. So, right here we found the sum. We know what that is. Now you take a limit as n goes to infinity of whatever sum you had. We've already worked this part down. We already have it. This part is 2 over n minus 4 over n. I could.
Negative 2
If I
over
really
n.
wanted
Then
to.
you have a negative in there, you don't want that.
It doesn't really matter. We can, yes, absolutely. Yes, you're right. For sure. I just didn't see it. Because I know what the answer is going to be. Are you okay getting that far then?
Yes.
We have a negative 2 over n, yes?
Yes.
Now, you take a limit as n goes to what? This is very simple. When n goes to infinity, where does that go? 0. It's weird. You mean the area is 0? Yes.
Because we're
Yes.
negative area.
Here's what.
Your positive area.
You need to think about what this is. This was a lot of work for something very, very simple. Honestly, it was. You're going to see this. If you didn't really picture what this graph is beforehand. And you will now. This says y-intercept's -1, the slope is 1, and you're going from 0 to 2. That's your picture, yes? It's just two triangles. 0 to 2. Why did our area go out to 0?
Because you're positive, you're positive or negative or say.
This is positive or whatever. This is negative, but it's the same exact value, only negative. In fact, it was 2 and -2. You know how I know that? Well, you could, or look here. This is positive area. This is subtracting the area that's below. That's going to give you a 0. These ones go to 0 because you're divided by infinity. It goes to 0. Gone.
There's totally a simplified version of that.
No.
It's gonna be like
Never.
power rule. Go through all the mess and display the power rule.
Never. Do you understand the reason why this is 0, ladies and gentlemen? Do you see why? The areas are both on the numerator and denominator of your whatever. Actually, it's not 2, is it? It's 1 times 1 over. It's 1/2. I don't know why I got the 2. But the area here, if you actually did the work, base times height over 2. I think it said 2. I meant 1/2. It doesn't quite match up to that apparently. That's 1. That's 1. So 1 times 1 is 1 divided by 2, or base times height over 2. You get 1/2 above, you get 1/2 below. That's what makes it 0. You okay with it?
Yeah.
Sounds cool.
Shall we do one more?
Yes.
The worst I can think of so far?
Yeah.
There's worse ones on your homework, I know that. But
Yes.
so that I can think of so far. Here it is.
You'll get inspiration after you see our homework.
Yeah.
You're inspired by terrible things. We're on to the next semester's class. Every semester the problems get harder.
They do. Yeah, they do.
Do they really? That's horrible.
No, not really. Not anymore. They used to though. So I kept seeing stupid mistakes. You guys got to be freaking kidding me. I'm gonna punch you more. Ha 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 ha. So make them harder. Harder.
I wish I could take this class the first semester you taught it.
It's very easy. Taught in high school.
You know, there can only be one Highlander.
There could be only one Highlander.
Oh, yeah.
I should just say go, do it, have fun. But we'll do it together so you can see it. But you need to be participating. You need to basically be able to tell me what to do, because when you get this on your test, and you will, you'll need to know how to do it, right? And if it makes sense what I'm doing, of course it does. I'm the teacher. I know what I'm doing most of the time. So it's gonna make, I do. It's gonna make sense when I do it. But when you go home, you need the practice. That's why when you skip your homework, or you skip pieces of your homework, it kills you, because you get to the test. You gotta realize there's only 10, 12 problems on the test, right? We have like 5 to 6 homework assignments, usually. So that's 1 to 2 problems on the test that come from your homework. So if you miss a homework, you miss 1 or 2 problems. Or at least you haven't practiced them. That's why your grades go down. So You need to practice it, even though it's hard. Practice it. Now we're going to go through every step. I've given you 5 steps for a reason so that you follow them. Step number 1 is what?
Delta X.
Y'all should find it right now. Delta X is refreshingly easy. Always. It's just subtraction over a number. So in our case, you get 1 minus 0 over n, 1 over n. Did you get 1 over n as well? Okay. What's the next thing that you do?
Find CK.
Okay, go ahead and do that. We're using right endpoints. Did you find C sub k already?
Yes.
It should go pretty quick. This is not one of those hard ones either. You plug in a number for A, you plug in nothing for K, you plug in delta X for delta X. 0. K, 1 over N. Did you get that too? So you got K over, did you get K over N? Do you see why right endpoints are kind of nice sometimes to use? Because you don't have the K minus 1, you don't have the 1 minus 1/2, that's even nastier. So right, I like right endpoints personally. K over N. Satisfied so far? What's the next thing that you do?
Function is, yeah, picture it.
Okay, do it. Find the function. I'll give you a minute for that one. By a show of hands, how many people made it that far? Am I right?
Yeah.
Oh, good. Then you're all right. That's fantastic. If you made it that far and I made it that far, hopefully we both did right. Did you get that as well? Cool. What would have made it worse? What type of endpoint would have really made it worse?
Left.
Left ones would have made it worse. Midpoints would have made it worse too, because you'd be cubing K minus 1. Not horribly, horribly bad, but you'd have more things to deal with. That's why this was such a pain, because you had this mess, right? That mess kind of stunk it up a little bit. Not hard, just more work. Just more
You
work.
could also do like K to the third over A to the third and put your cube root inside of it.
From right here? Well, I'm saying if I had that. Okay, that would have made it worse. That's what we were talking about. What would have made it worse than this?
Okay.
A left endpoint or a midpoint would have made this problem a lot harder. Are you okay with that one so far? What's the next step you do? Do the sum. Do the sum. I don't want to write up there until you at least have something on your paper, so go for the sum. You probably should have a bracket. If you don't have one, put one on your paper. Get in the habit of doing that, because you're not just multiplying this last little bit. You're multiplying the whole thing by delta x. Whatever the delta x happens to be, in our case it's K over N. Oh, 1 over N. So, geez, shoot, you know, I looked right there, I'm sorry. By the way, I just meant to do this to test you. You guys are, oh, yeah.
You always
screw
do that.
You're not buying that?
You always do.
Darn it. I'm so good at doing that though.
Yeah, I see it every time.
Yeah, okay, 1/n. Yeah, my bad. I was kind of looking at that and wondering how are we going to deal with the k to the 4th, but I'm sure we would have dealt with it at some point. Anyway, do you feel okay with this so far? Raise your hand, feel just fine with it. You have that on your paper, exactly like that. Cool. Now what? Probably make it a lot prettier. Before you can split anything, you have to deal with this multiplication. You can't split this up right now, it's being multiplied. So you have to distribute that. You have to think about this as k cubed over n cubed, so eventually you'll split it off. You have to move this 2 to the top or take that completely out later. I'd probably move it to the numerator right now just to be able to deal with it a little bit easier. So I'm going to multiply by 2, that's 2k over n. I'm going to multiply by 1/n to both of those, and I'm going to make that k cubed over n cubed. That's our next 3 steps.
Is it okay if we'd already done that step previously?
Over here?
Yeah, I did.
Yeah, that's
I did
fine.
the 2 into K and then cubed everything much earlier and just kept carrying it out that way.
So I've made things nicer inside. Now I'll distribute that 1/n. And what we'll get is 2k over n squared minus k cubed over n to the 4th. And that should be in a parenthesis signifying that I'm taking the sum of that entire expression, not just the first part, not just the second part, the whole thing. Okay, now what would you like to do?
Pull out
Now you split it up. You can't pull out any k's yet. You can't. Unless you factored, you could do that, but that's probably not the easiest way to go. What we should do here is split these up into 2 different sums and then pull out all the constants. Are you following me or not? You sure? Remember, this is easy because I'm doing it. When you get home, you need to follow the same steps. Why don't you go ahead and try to do the rest of this on your own? What I'd like you to do is take out everything that doesn't have to do with a k in front of your summation. Use the appropriate formula that I've given you from before, figure out that closed form, and then simplify it. After you simplify it as much as you can, then take a limit. I'll give you about 2 minutes to see if you can work on it. I'll do about 1 step every 10 or 20 seconds or so, just to make sure you're on the right track. So look up here at the board every once in a while and you'll start seeing the steps. you make it that far on your own? Simplifying the first one, squaring everything inside the parentheses of the second one, multiplying by 1 over n to the fourth. Just make it that far. Yeah. Yes, no.
Why isn't it cute?
Why is it what cubed?
The second part?
Did I mess the formula up?
Well, over there it's K cubed.
The formula for K cubed is n plus
That's
one.
what I was wondering at. I thought that formula right there was going to be cubed.
I don't believe so.
That's the-
Unless my mind's completely flipped off out and I've lost, flipped off. My mind's flipped off. It is flipped off today, I don't know. No, I believe it's squared. N times n plus 1 over 2, quantity squared should be the formula I gave you. If you have a cubed, you might want to change it back. It's not cubed. Satisfied so far? Some of you look lost algebraically. Are you okay? All right. I'm going to keep going.
Where did the 4
Yeah,
come from?
how do you get 4?
Why'd you get n plus 1 over 4 and not n plus 1 over n?
Oh, this one?
Yeah.
I was testing you. You passed.
Okay.
That's 2. Because I saw that 4 and that's what I did. Yeah, thank you. I'm sorry about that, guys. My bad. Yeah, good catch. Thank you. That's why I ask you. Because I do this stuff too. Is everything else right? Check out? Okay. please notice something that's going to happen here, the algebra. We're subtracting that entire last fraction, right? So when you subtract that entire last fraction and you split it up, it's not going to be plus 2n over 4n squared. It's going to be minus 2n over 4n squared. You see that? This will, by necessity, distribute when you split that up. It has to. So you're going to get minus 2n over 4n squared minus 1 over 4n squared. Do you see why? Do you see why? Yes or no? For instance, I can show it to you this way if you want. 5 minus 1 plus 3 over x, like that, would be 5 minus 1x plus 3x, right? Like that. That's what that means. So this would distribute to both those. That's the same thing. We're just using it 3 times here. Okay. Let's simplify. Unless I've made some sort of error, I think that's about what you get. Was anyone able to make it down that far on their own? Good. Good. If not, where did you make a mistake? Find out. Was it a sign? Was it simplification? This is all about your algebra. Notice we basically stopped doing the calculus after that part, finding the formula, and then this is all just some basic algebra. Now it comes back in the calculus. Once you get this right, we're going to take a limit. That's the last thing we'll do. So step number 5, I'm just going to write right here. It's already nice and broken down for us. That's what's great about this. We didn't have to find a common denominator and divide everything by the largest power of the denominator. You can do it that way. It's a little bit more concise. This says, all right, the area, not an approximation anymore, the actual area, because we're taking n to infinity. It says pack as many rectangles as possible and then some into that area. That means there's not going to be any error whatsoever. You're going to get, well, what's this go to? This one?
No.
That's a constant. What's this one go to? What's this one go to? This one? This one? How much?
3/4.
That's what we're talking about.
So we don't have to recombine all of our fractions for a single.
Heck no, no, why would you ever do that? Oh my gosh, no.
I guess because I hate myself on the
Because you hate yourself on the homework. Because you want to waste time. Take your limit. Then if you have to do it, combine them. You don't have to. This is so nice. A number over n, that works out very nicely for you, right? So use it, shoot, why not? Why not do it that way?
Under what circumstances would we have to recombine them?
I can't think of one.
Okay.
So don't do it.
I can't
think
stab
of
myself in the face in my pants.
Well, the only time you would is like, for some reason, if you wanted to combine these and make a common denominator, or if you didn't want to split this up, you could do it here, okay? Minus the limit of this, divide all this by n squared. And then you can do the same thing there. That's fine. I don't care how you do it. I'm just showing you that you can split it up. It comes out very nicely. Then you have less work to do on your actual limit. The more you split up like this, and have one term, it comes out just a piece of cake. No work on the limit, more work on the algebra. Or less work on algebra, more work on limit. Either way you go, you're going to get it right, provided you know how to work with this appropriately correct sign, and you also know how to do your limit. Good. You raise your hand, feel okay with getting the 3/4 there. All right. Now, the next thing we're going to talk about, it's honestly going to take me about 2 minutes to really go over it. Then we'll start